is one easier than the other? So let's see this function. So I want to take the integration of x divided by 5 plus xy squared, where the integrating region is 0 is less than equal to x, less than equal to 4. 1 is less than equal to y, less than equal to 2. Okay, so this is the function. Okay. As long as your integrating region is a rectangle, immediately you know you can write down this in two different forms. Taking integral with respect to x and then y, or dy dx. You have two different ways to go. All right. If you choose to go dx dy, you need to find the antiderivative of the integrating function with respect to x first. All right. If you choose to go for dy dx, you need to look at this function and try to find the antiderivative where y is the variable. All right. So what I'm saying here is, for the same function, regarding different variables as the only independent variable, finding the antiderivative can be very different. Okay. For instance, if I'm asking you what the antiderivative is for this function, when x is the independent variable, it's not going to be easy. Right? It is not going to be easy because you have both x in the numerator and the denominator. All right? So if x is the variable, y is the constant, the antiderivative for this function is not going to be easy. However, if I'm regarding x as a constant, it doesn't really matter where it is. All right? If y is the only independent variable, then I can easily find the antiderivative function for this fraction. Okay? So I'm saying this route is going to be significantly easier than the first one. Okay? However, you can try to go both of these and see whether you can end up with any. If you go for dx dy and you try really hard to find the antiderivative for half an hour, you didn't find any, and you're stuck over there. What's the hint that you want to take?
Switch.
You don't spend half an hour at all. You just spend probably 2 or 3 minutes. If you cannot find the antiderivative, immediately switch the order and see you can do the other. Okay? So because you have 2 ways to go, there are cases one way is much more easier than the other. So this is going to be much more harder. So I can write down it. So 0 to 4 goes inside, 1 to 2 goes outside, and x 5 plus xy squared. I'm staring at this function for 2 minutes, and I couldn't get up with any antiderivative function, and I just give up. Right? I can switch the order from 0 to 4, from 1 to 2, x5 plus xy squared. And then I need to find the antiderivative function for this function where y is the only independent variable. So what do we have? So at least I want to try the function looking like this, 5 plus xy. All right? So if I take a derivative with respect to y, I'm going to get I'm going to minus 1 over 5 plus xy squared and then multiply by x. All right? But I have a plus here, so I want to have a minus sign inside. So this becomes a plus. So this is indeed the antiderivative function. There are different ways. It's up to you. There are different ways to find the antiderivative. Really, it's up to your own habit. So my way is I usually just go try and see whether I can take the derivative and end up with the function I had. Okay. So this one is pretty safe. I can make sure this is indeed the antiderivative. Okay. So this is the antiderivative function where y is the only independent variable. So minus from 0 to y is equal to 1 to y is equal to 2. From 0 to dx. Okay? Okay, and then I need to evaluate the inside. When y is equal to 2, I'm getting a minus 1 over 5 minus plus 2x. And when y is equal to 1, I have minus 1 over 5 plus x dx. Right? So this is what we have. No matter how complicated it is, okay? No matter how complicated it is, listen to me carefully. A lot of people get confused in evaluating double integral. As easy as this kind of examples. No matter how complicated it is, after you simplify the interior integral, you should end up with a function involving only x. So I should see no y at all in here. Okay? So if you're still having y in this single variable integration, that means there's something wrong here. Okay? So there should be no y variable at all. Okay? Otherwise, there's no way for you to go even further. So after you evaluate the interior integral, you already eliminated one of the variables, which means the following integration should have only one variable appearing in there. Okay? So listen to me carefully. Here is a very crucial step. A lot of people evaluate the one variable and then you end up with a function involving still y, and they don't know how to do in the following. You have to eliminate the one variable to go beyond. So here, I can eliminate x by taking the integral again. All right? You can combine these two fractions, but you don't want to do that.
Why?
Because when you combine the fractions, you get a big fraction. In order to evaluate the integral for that big fraction, you still have to break it into two. Remember, you have this method before. All right? You have this, what is the method here? Breaking into fractions, kind of a partial fraction method, right? On the other hand, these two functions, I can easily find the antiderivative, right? Their antiderivatives are all log functions, all right? So the first one is going to be from 0 to 2. So minus 1 over 5 plus, oh, sorry, minus 4. So plus 2x dx, then plus from 0 to 4, 1 over 5 plus x dx. So I can easily find the antiderivative for this guy is 1/2 log 5 plus 2x. And then I have a minus right here equals minus evaluating between x equals 0 and x equals 4. And then plus log 5 plus x evaluating from 0 to 4. Okay? So
why is it negative 1/2? Because of the 0 and 10?
yeah, so when I take the derivative with respect to x here, I'm going to get 1 over 5 plus 2x. The multiplied by 2 is going to cancel, it's 1/2, and the minus that right here.
Yeah.
Right? And you can do the following. Just plug the numbers. Okay? So in order to do double integral or triple integral in the future, we need to be able to identify the region and study the region correspondingly if it is one of the 5 different types. And throughout this evaluation, I need your whole arsenal of your skills in doing single variable calculus. Okay? Finding the antiderivatives, changing variables, breaking into different fractions, all these kind of skills are still required here. Okay? Questions? So I want to give you one more question so we can begin our reviewing section. So you can think about the questions you're going to be expecting in the end, right? Taking derivatives. You're not going to get a question saying, here is a function involving 2 independent variables. Compute the partial derivatives. These questions are too straightforward and nothing is going to be tested over there. They have to test you to compute the partial derivatives and then the applications. Right? So how do you use partial derivatives to tell what the function looks like? Similarly for double integral as well. They're not going to give you a simple question involving this kind of simple double integrals. You can choose one of the routes to go and immediately you get the answer. They usually will give you a question liking this. One of the orders is much easier than the other. So they will test you how you can find the antiderivative, and if you cannot, what kind of other alternatives you can go. Okay. So next one I want to go is this function. I want to take the double integral for 3x divided by cosine squared xy dk, where x is between square root of pi over 2 and 0, y is between 0 and 2. Okay? This is what I want to have. Again, as long as your integrating region is a rectangle, immediately you have two different orders. You can do a single variable integration. Either it is dx dy, which means I need to find the antiderivative with respect to x, or dy dx, where I need to find the antiderivative with respect to y first. So we already had experience over here, right? If you see functions including variables x in the top and the bottom, these kind of functions is usually difficult to compute its antiderivative. If you only have the denominator or the numerator, the other things are only constants, it's much more easier. All right? So what I'm saying here is this is still going to be much harder than dy dx. I can find the antiderivative for this function where y is the only independent variable easily. Okay? Which means I just need to find the antiderivative of 1 over cosine squared. Am I right? 1 over cosine squared. As long as I can do that, then I can make my modifications to make sure the derivative is equal to this fraction. So what is the derivative for cosine squared, 1 over cosine squared? Cosine squared t. Tangent t. So if you the derivative for tangent t, you're going to get cosine squared t, right? You can write tangent sine over cosine, and then using the quotient rule, this is easily going to be the case. So I want to have tangent xy as my antiderivative, and with some modification here. If I take the partial derivative with respect to y, I'm going to get 1 over cosine squared xy, all right? And then x is the constant, so I have to multiply by x, but I need a 3 right here, so it's going to be 3. This whole thing is going to be the antiderivative. Okay? So if you are not convinced, you take the partial derivative with respect to y. All right? So this is how you verify whether your antiderivative is the correct function. If I take the partial derivative with respect to y, this is going to give me 1 over cosine squared xy, then multiply by x multiplied by 3, which is exactly right over here. Okay? So in a lot of cases, this step is quite necessary for you to verify your answer is correct. Okay? And then I need to evaluate y goes inside. So x is from 0 to square root of pi divided by 2. Y is from 0 to 2, so this is going to be evaluating from y is equal to 0 to y is equal to 2. So the first order dx dy is completely useless here. Okay, I just need to go for the other. Okay, so this is the thing. So y equals 0, I'm going to from 0 to square root of pi divided by 2 is 3 tang 2x. All right. Then minus 3 tang 0, which is just a 0. 0 dy. So this disappears. So I'm evaluating from 0 to square root of pi divided by 2, 3 tang 3x dx.
2x.
Oh, 2x. 2x dx. Okay? Again, I can check one more time. After I evaluate the interior integral, I'm getting a function involving only x, so I feel safe here. Okay? I don't have to deal with y anymore because you already have done the interior integral with respect to y. You're supposed to eliminate the variable y. Then I need to find the corresponding function where you take the derivative, you're going to get a tangent function. What function, if I take the derivative, I get a tangent function? Or sine t over cosine t. I want a 1 over, so definitely I want a log. All right? So I want a 1 over cosine, so I want a log cosine t right here. But I have log cosine t taking derivative. I have a 1 over cosine t multiplied by minus sine t. So I want to have a minus sine again right here. Right? So the antiderivative for this whole thing is going to be 3 divided by 2 minus log of cosine 2x. Evaluation from x equals 0 to x equals square root of pi divided by 2. Why am I having square root of pi divided by 2? Doesn't give me anything nice. I think I copied it wrong. So you're supposed to have pi divided by 3. This one we can evaluate the cosine value, so it will be easier question. So pi divided by 3. Pi divided by 3. And pi divided by 3. So in the end, I need to evaluate pi divided by 3. Okay. Again, if you're not very sure about this antiderivative you found, what you can do is take in derivative with respect to x and see whether you can end up with 3 times 2x. So if I take the derivative, I have 1 over cosine 2x multiplied by minus sine 2x and multiplied by 2. I'm going to cancel the minus sign, cancel the 2. I end up with 3 sine over cosine. This is exactly what I have. Right? So this is indeed the antiderivative. So when I plug in x equals pi over 3, I'm getting minus 3 divided by 2 log cosine 3 pi 2 pi divided by 3. Then minus 2 divided by 3 log cosine 0. Cosine 0 is just 1, but log 1 is just 0. So the second part is going to disappear. The first one, cosine 2 pi divided by 3 is going to be, what is cosine 3 pi? I'm going to get a negative